3, whatever I just said, is pretty darn close to 10, but it's less than 10, and so therefore it's going to, the log of it's going to be less than 1. But in any case, we don't really care. We've got devices these days for doing these calculations for us. Be very thankful we have these devices. Once upon a time, such devices, in fact, did not exist, and people had to calculate logarithms by hand, but we don't have to do that, so we're not going to worry about it. In fact, there is a type of graph paper that you can buy that allows you to, in fact, in a sense, generate one of these log linear graphs, one that's a lot like this, without having to actually calculate the logarithms. And this is very useful if you're living in a world where you can't use all of these computational devices to determine your logs, but we can, so we're not going to really worry about that. Okay, so were we to take this graph and put it over here and use log of number instead of number, then our exponential decline looks like this. Now that should look very familiar, right? Because I drew it so it would be identical to this one, because that's what you'll see. And in fact, your exponential growth will be the same. That little curve down there is unintentional, okay? So if you are, in fact, seeing exponential decline, and you've graphed out what you are working with on log linear graph paper, in other words, if you've graphed the log of the number as a function of time, then you should see, if it's exponential decline that you're seeing, a straight line. Or if it's exponential growth that you're seeing, a straight line. Again, all I've done is I have, hypothetically, taken my numbers and done some kind of log function in a calculator or a spreadsheet or whatever, or if you're really impressive in your head, and taken those numbers and graphed them out, the log of the numbers, against time. Time is, in this case, the standard time. It could be minutes, could be hours, whatever. But it's linear. It's going 0, 1, 2, 3, 4, 5. Not log, just those would be, for example, minutes. We get this nice straight curve. Now, if we don't get a straight curve, for example, we might see something like this, where that's supposed to be more or less flat. Where instead of continuing to go downward, you have some plateauing out of the decline. And what that is indicating is that you have organisms that for some reason are resistant. They're either resistant because they're less susceptible to whatever you're treating them with, or the treatment is not as able to actually physically reach them. And so you'll kill the susceptible off at a nice exponential rate, but then you reach a point where you're no longer having exponential death. Alternatively, it's conceivable to have a shoulder, where the organisms, I'm going to try to make that flat, where the organisms are displaying some amount of inherent resistance, whatever you're hitting them with, until that level of resistance is overcome, and then you see an exponential decline. So if you've got bacteria and you're treating them with UV radiation, you're actually going to have a shoulder here, because they can take some amount of UV radiation exposure before they start dying. But once you've overwhelmed them, then you'll see the standard exponential decline. And this has to do with target theory, that basically when you're hitting things with discrete something, that a certain number of hits of that something is going to be necessary to kill them. And you're going to have the number of hits that the bacteria receive Poissonally distributed, so some fraction of them, in fact, is not going to have enough hits so that they actually are killed off. And that's why you don't suddenly see the organism instantaneously being gotten rid of. It takes time, and that time represents the probabilistic nature of treatments. Treatments, even if their chemicals are discrete, it's individual chemicals, the organism has to be exposed to a certain amount of them for a certain amount of time to mess up its physiology enough so that, in fact, the organism dies. So over here, we can also draw another curve, making dashes so it's easier to see. So that curve you'll see is less shallow than this curve. And so what's going on here? Well, one possibility is that we're using the same treatment, but we're using it to a lesser extent. So it could be a disinfectant, and we're using it at half strength. And that here has the effect of simply killing off the organisms with exponential death, but the rate of killing is lower. Either that, or maybe we have doubled the amount of disinfectant, for example. Now, there are potentially problems with doubling the amount of disinfectant. It might not work as well as you expect it will work, or by using that much chemical, it might be damaging to whatever it is that you're treating, more so than if you use less chemical. But let's say we used twice as much, and now we're seeing a steeper rate of decrease. So this is still an exponential decline, but it's a steeper one. And that simply means that per unit time, we're killing off organisms more rapidly. Also over here, if we started with this concentration of whatever it is we're treating with, and we started with 10 to the 2 individuals, I mean, I'm trying to draw those two lines parallel. You can see this idea that if you started with a greater number of individuals, it's simply going to take you longer until you've reached some level of killing of the population than if you started with fewer individuals. So you're seeing the same rate of decrease, but it's an exponential rate of decrease. So just like over here, we killed off that population. Again, we using whatever concentration of the killing agent that we used in here for the treatment of that population. We're getting simply a rate of killing on an exponential scale that's identical. It's just that we're starting at a lower level, so we're going to reach a lower level faster, or some lower level faster. And if you drew these here, over here, we would see curves that look more like this. So it's a slower rate of killing versus this. I suppose I should draw that with dashes. Or alternatively, if we started down here, we would see something that pretty much is parallel to what's above it. That's harder for me to draw, which is representing, comparing that curve with that curve. Okay? So what we're talking about is control of microbial growth. General principle is that when we are controlling microbes and we're trying to kill them off, we're typically able to reduce their numbers in a way that is exponential. An exponential death is observed. The steeper the curve, the faster the organisms are being killed off. The fewer organisms you start with, then the sooner you're going to reach some certain lower level of organisms because you're simply starting with fewer, even if the rate at which you're killing exponentially is the same. And also, if you should happen to have organisms that for whatever reason are more resistant than other organisms in the community or population that you're treating, then you're going to have some kind of leveling off in your killing. You're going to have at best a biphasic curve where one set of organisms is more susceptible and it's killed off rapidly, and then another set of organisms is less susceptible or not susceptible at all, and it's killed off less rapidly. So the curves, there's actually two curves being represented here. Lower rate of killing off and higher rate of killing off. And you're not seeing the lower rate of killing off because you're not distinguishing among the different types of organisms. And so until you've killed off the more susceptible ones, you're not going to be able to even see in a curve like this the rate at which you're killing off the less susceptible ones, unless you're able to, in fact, distinguish between these two. So that's all I think I wanted to talk about in terms of exponential death. Again, the chapter is the control of microbial growth. This is, I guess, the general principles of control of microbial growth.